In the previous lecture, we have discussed about the moment area method and an illustration of that to find out the slope and deflection of a cantilever beam with UDL throughout. And now, in this lecture, I am going to give you more illustrations of the moment area method which are going to be useful results in the flexibility method as well as stiffness method later. Let us go back to the same cantilever beam like this. AB is the cantilever beam, A is a fixed support, B is the free end of the cantilever, E, I, L are the properties of the beam. If I apply a moment here, say a clockwise moment at this end, capital M, the bending moment diagram would look like a rectangle. The moment M will be same throughout the beam, and the bending moment is going to be hogging in nature if I apply it this way. Now, if I try to calculate the slope and deflection at the free end B, that is the deflected shape of the beam. This point is the deflected point, say B prime. As before, we can define this angle as the slope and this distance as deflection delta B. If we apply the first theorem of moment area, the slope theta B will be equal to the angle between the tangents drawn to point A and point B as in the previous discussion, and that is equal to 1 by EI into area of the BMD between the 2 points A and B. So area of the BMD is M into L. That is it. So this is equal to M L divided by EI. Deflection delta B is equal to, as per second moment area theorem, the deviation of the tangent drawn to point B and point A is given by 1 by EI times the moment of the bending moment diagram between the 2 points with respect to B, and that amount will be equal to the deflection delta B, because the tangent drawn to point A is always horizontal. So delta B is equal to 1 by EI area of the bending moment diagram, that is M into L, M into this L. Center of gravity or centroid of this would be at the center of the diagram because it is symmetric. So this distance will be equal to L by 2 for sure. To get the moment of that about end B, we multiply that with L by 2. So this is equal to M L square divided by 2 EI. Further, so the same cantilever beam subjected to an end point load, the capital W, reflected shape like that, slope theta B, deflection delta B, here theta B will be equal to 1 by EI. Bending moment diagram in this case is going to be a right angle triangle. Let me draw that for completeness. The bending moment at this end is equal to 0. It gradually increases from here to here as W into the distance x, anywhere in the portion BA, and when you reach here, the bending moment is equal to W into L. The variation is linear. Now, theta B is equal to 1 by EI into, of course, this is a Hawking bending moment diagram, so we have a minus sign over here. 1 by EI into area of the BMD, 1 by 2 into L into WL. And this is W L square divided by 2E. Further, deflection delta B is equal to the moment of this BMD with respect to end B divided by EI, because tangent drawn to point A is horizontal and the deviation of the tangent drawn to point B and point A will represent delta B. So delta B is equal to 1 by EI W L into L, WL square divided by 2, that is the area of the BMD. Centroid may be somewhere here. Distance to the end B will be equal to 2L by 3. So this is equal to, you can cancel 1, 2 from here, W L cube divided by 3E. We may require these results in the flexibility matrix method as well as stiffness method later. Now, if we go to a simply supported beam, a beam supported by a hinge at one end and a roller at the other end, subjected to UDL throughout, uniformly distributed load throughout, of intensity W per meter. Properties are Young's modulus, second moment of area or moment of inertia, length. The bending moment diagram of this beam would look like bending moment is equal to 0 at both these supports, and the variation of bending moment diagram will be like a parabola between these 2 points. If you take any section in between B and A, say distant x from end B, with the support reactions being equal to W into L divided by 2. The total load is W into L, that is shared equally between the 2 supports because of symmetry. So bending moment at this section is W, let us say that is M into X. So M suffix X. That is equal to W L by 2 into X sagging and W X into X by 2 hogging. The bending moment of this portion of the load is going to hog the beam, and this reaction is going to sag the beam at this section. So we have a minus sign for hogging and plus sign for sagging. That is the equation for BMD. And if you follow that, the variation will be, you can see that the variation is going to be parabolic, second degree. So finally, if you draw the bending moment diagram, you are going to get maximum ordinate at the center equal to W L square divided by 8, and the bending moment diagram will be like this. Now here, let me draw the bending moment diagram a bit below. Center, like that, W L square by 8. Now, we are interested in finding out the slope and deflection If I draw the reflected shape of this beam, maybe like that. If I draw a tangent to the elastic line at this point, end A, it may be like this. Tangent drawn to elastic line at B would be like that. So this distance is defined as the deviation of the tangent drawn to point B with respect to that of point A. We define that as D, A on top and B below. Deviation of tangent drawn to point B with respect to that of point A. Now, the slope at point A is defined as this angle, say theta A. We can define the slope theta A as equal to the deviation dBA divided by length, the span of the beam. The deviation being a small number, dBA divided by L will be equal to tan theta, and for small theta, tan theta is approximately equal to theta. So theta is equal to dBA divided by L. Now we can find out dBA using the second moment area theorem. So this is equal to, let us put 1 by L here. dBA is 1 by EI into the first moment of the bending moment diagram with respect to this end. So area of the bending moment diagram is 2 by 3 into L into W L square by 8. Centroid will be at the center because of symmetry. So distance to the right end will be equal to L by 2 multiply with L by 2 to get the moment. That reduces to, can cancel 1, 2. 1 L can be cancelled like this. So what remains is W L raised to 3 divided by 24 EI. You can observe that the slope at this end is clockwise and the slope at the other end is anti-clockwise, and the number is equal to W L cube by 24 EI because of symmetry in this case. So theta A and theta B are same but with opposite signs.